In section 6.1, we saw that we had systems of equations in two variables. When we had two variables, those two variables defined a line. When we looked at the graph of the two variables, it was possible that those two lines could intersect at one point, giving us only one solution. Those two lines could actually be the same line, giving us an infinite number of solutions. Or the two lines could be parallel, meaning that we had no solutions. When we had only one solution, our answer was an ordered pair x, y. Now that we're working in three variables, those three variables define a two-dimensional plane. When we talk about graphing a two-dimensional plane, it's possible to have only one solution, and that solution would be an ordered triple x, y, z, where all three planes intersect. It's possible we could have infinitely many solutions, and that happens when all three planes intersect in a straight line. It's also possible that we could have no solutions or an inconsistent system if all three planes are parallel, or if two of the planes are parallel and crossed only by one, or if none of the three planes intersect more than two at a time. When we're solving a system of linear equations in three variables, our first step will be to eliminate one of the variables, such as x, from two of the equations. Remember, I told you in section 6.1 that when you're solving a system of equations, the number of equations has to be equal to the number of variables. So if we're looking at three variables here, that means that we need a minimum of three equations in order to solve this system of equations. Once we eliminate one of the variables in step 1, then we're going to apply the same techniques that we looked at in 6.1. Step 1 is to eliminate one of the variables, such as x, from two of the equations. Once we do that, we now have two equations in two variables, and we use the techniques from 6.1 in order to solve. But if there's no solutions for y and z, then the given system also has no solutions. If there are infinitely many solutions for y and z, then we write y in terms of z and proceed to step 3. Step 3 is to substitute the values for y and z in one of the given equations in order to find x, and then the solution will be x, y, z. And we'll want to check our answers as we did in the previous section. In order to help with the organization when we're solving problems, I'm going to number my equations. So I'll call this first equation 1, the second one 2, and the third one 3. Looking at these equations, I have to pick a variable to eliminate. So I'm going to start by eliminating the x's because I have a positive and a negative x here. It seems to me that would be easy to do. So using equations 1 and 3, I could just add those two equations together. And when I do, I have x minus y plus 2z equals 6, and negative x minus 2y plus 3z equals 7. When I add these two equations together, I get negative 3y plus 5z equals 13. This is a new equation, and just for organizational purposes, I'm going to call this equation equation 4. Then I'm going to use equation 3 with equation 2. So that means that I need to multiply equation 3 by 2 in order to eliminate the x's. So I'm going to have equation 2 plus 2 times equation 3. So equation 2 was 2x plus y plus 3z equals 7, and 2 times equation 3 would be negative 2x minus 4y plus 6z equals 14, because I had to multiply every term in this equation by 2 so that when I added the equations together the x's would cancel out, and that's going to give me negative 3y plus 9z equals 21. I'm going to treat this as my equation 5. Now I take equations 4 and 5 and I consider them as if they're their own system of equations. So looking at the system of equations that's left after I eliminate x, I'm going to use the same techniques that I used in 6.1. One of the easiest ways to solve this would be to use elimination and eliminate the y's. In order to do that, I could multiply this first equation by negative 1, and that would give me 3y minus 5z equals negative 13. And then this equation I'm just going to write down as negative 3y. Just carry it across as it is. And now when I add the two equations together, the y's are going to drop out, and that's going to leave me with 4z equals 8. And if I divide both sides by 4, I get z equals 2. There's a value for z. Now I can go back to equation either 4 or 5 and solve for y by plugging in this into, I'm going to use equation 4, and that gives me negative 3y plus 5 times 2 equals 13. Simplifying this gives me negative 3y plus 10 equals 13. Subtract 10 from both sides, and I get negative 3y equals 3, and that means that y is equal to negative 1. So now I know values for z and for y. I have to go back and find x. And I'm going to use this first equation to plug in numbers for y and z and solve for x. So that's going to give me x minus, and then y we said was negative 1, plus 2 times 2, because z was 2, equals 6. Now I just simplify, and that gives me x plus 1 plus 4 equals 6. Combining your like terms gives you x plus 5 equals 6, and when we subtract 5 from both sides, we get x is equal to 1. That means that my final answer will be the ordered triple: 1 for x, negative 1 for y, and 2 for z. And if we take these numbers and plug them into any one of these equations, I must get a true statement. Let's check one right fast. So if I plug in a 1 here, that would give me 1 minus a negative 1 plus 2 times 2 equals 6. And I want to know if this is true. Well, that's 1 plus 1 is 2 plus 4 is 6, and that works out. Just to make sure it wasn't a fluke, I'll go ahead and check the second equation. That's 2 times 1 plus negative 1 minus 2 times 2, and I want to know, is that equal to negative 3? Well, that's 2 minus 1 is 1, and 1 minus 4 is negative 3. That checks out. And we might as well check the last one while we're here, so that'll be negative 1 minus 2 times negative 1 plus 3 times 2, and we want to know, is that equal to 7? So that gives us negative 1 plus 2 is 1, and 1 plus 6 is 7. That checks out. So we're able to check all three of our answers, and that would be our answer to this system of equations. In example 2, we're told that 1,000 tickets were sold for a total of $15,500. The price of the tickets were $10 for children, $15 for students, and $20 for adults. There were 200 more student tickets sold than adult tickets sold. Find the number of each type of ticket sold. First thing we have to do is we're going to need 3 equations because we have 3 variables, because there's 3 types of tickets. So what I'm going to do is I'm going to let C represent the number of children's tickets, S will be the number of student tickets, and A will be the number of adult tickets. Because I have 3 variables, I need 3 equations. Fortunately, they've given us enough information in this problem to write those 3 equations. We're told that a total of 1,000 tickets were sold. So that means the number of children's tickets plus student tickets plus adult tickets is equal to 1,000. Also, we were told that a total of $15,500 was made. So I take the price of a child ticket times the number of children's tickets sold, plus the price of a student ticket times the number of student tickets sold, plus the price of an adult ticket times the number of adult tickets sold, and that must be equal to 15,500. And then lastly, we were told that there were 200 more student tickets sold than adult tickets. The number of student tickets would be equal to the number of adult tickets plus 200. This would represent the system of equations that I want to use to solve to find each type of ticket that's sold. Because I have S by itself right here, I figure I can plug this in place of S in these 2 equations and have 2 equations in terms of 2 variables. So that's what we're going to do. So we're going to use this to rewrite this system of equations in terms of 2 equations with 2 variables. And that's going to look like this. I take C plus, instead of S, I write A plus 200 plus A equals 1,000. When I combine my like terms, I get C plus 2A plus 200 equals 1,000. Now I can subtract from 200 from both sides, and that gives me C plus 2A equals 800. This is going to be one of my equations in terms of 2 variables. To get the other one, I'm going to use this second equation, 10C plus 15 times A plus 200, because that's what I said I'm going to substitute substitute in place of s, plus 20a equals 15,500. Now I need to distribute this 15, and I get 10c plus 15a plus 3,000 plus 20a equals 15,500. Now I can combine like terms, and I'm also going to go ahead and subtract 3,000 from both sides, because what you do to one side you have to do to the other. And when I do that, that's going to give me 10c plus 35a equals 12,500. This is my second equation. So now I've worked this 3 variables with 3 equations down to 2 variables in 2 equations. So here's my 2 equations. At this point, I can either use substitution or elimination in order to solve. I've already used substitution once, so just in the interest of showing you a variety of different methods, I'm going to use elimination to eliminate the c's. And in order to do that, I'm going to look at negative 10 times equation 1 plus equation 2. So I'm going to multiply every term in this first equation by negative 10, and that gives me negative 10c minus 20a equals negative 8,000. And then I just write down equation 2 as is. That's 10c plus 35a equals 12,500. Now when I add these 2 equations together, I get 15a equals 4,500. When I divide both sides by 15, I get a is equal to 300. Now that I know what a is, I can go back to this equation and find c. So in equation 1, I have c plus 2 times a, but a we said was 300, equals 800. So that means that c plus 600 is equal to 800. And when I subtract 600 from both sides, that gives me c is equal to 200. So that means I had a total of 200 children's tickets sold and 300 adults tickets sold. Now I can use the answers that I have for a and c and go back to the original equation, the original problem, and solve for s using this first equation right here. So in place of c, I have 200 plus s plus 300, because this is the number of children's tickets sold and this is the number of the adult tickets sold. That has to be equal to 1,000. So when I combine my like terms, I get s plus 500 equals 1,000, and when I subtract 500 from both sides, I get s is equal to 500. What that means is, for this particular event, I sold 200 children tickets, 500 students tickets, and 300 adult tickets. So for this particular problem, your first step was to identify your variables, then write your system of equations based on the information in the problem, solve your system of equations, and then write your final answer in terms of the information presented in the problem. For the last example, we're told to solve the system of equations. In order to help us do that, I'm going to number these equations 1, 2, and 3. Let's pick a variable to eliminate. Well, it looks like x is missing from this third equation, so let's go ahead and eliminate x using the first 2 equations. So if I take negative 2 times equation 1 and I add to that equation 2, I should eliminate the x. So negative 2 times equation 1 gives me negative 2x minus 4y plus 2z equals negative 4. Equation 2 was 2x minus y plus z equals 2. And when I add these 2 equations together, the x's are going to drop out, the y's are going to be negative 5y, and 2z plus z is plus 3z, and that's equal to negative 2. This is a brand new equation, so I'm going to call this equation equation 4. So if I look at equations 3 and 4, I have a system of equations in 2 variables. I have 5y minus 3z equals 2 and negative 5y plus 3z equals negative 2. If I were to add these 2 equations together, notice this is equation 3 and this is equation 4. And when I add these 2 equations together, the variables drop out and the numbers drop out, and that means that I have a true statement. That means that this is a dependent system of equations. My solution is going to be y written in terms of z or z written in terms of y. I'm going to choose to write y in terms of z. So that means that I could take this equation, let's look at equation 3, and if I solve this equation for y, I get 5y equals 3z plus 2. And if I divide both sides by 5, that gives me y equals 3/5 z plus 2/5. Z is just going to be z. There's y in terms of z. And now I can go back to one of my other equations and solve for x. So I'm going to now use equation 1 to solve for x in terms of z. I knew I had an infinite number of solutions because this is a true statement, so I just wrote y in terms of z, and z is just going to be any real number. Now I need to solve for x. So I'm going to use equation 1 because the x is by itself here, and that should be easy arithmetic. So looking at equation 1, I have x plus 2 times y, but we said y is equal to 3/5 z plus 2/5 minus z equals 2. Now I'm going to distribute this 2 across here and simplify, and I get x plus 6/5 z plus 4/5 minus z equals 2. Now I have like terms that I can combine, and also I can subtract 4/5 from both sides. And when I do that, I get x plus 6/5 minus 5/5 is 1/5 z. The 4/5 are going to cancel out, and that's equal to 2 is 10/5. 10/5 minus 4/5 is 6/5. So I can solve this for x, and I would say that x is equal to negative 1/5 z plus 6/5. And the way that I would write my answer is, this is the ordered triple, negative 1/5 z plus 6/5, comma 3/5 z plus 2/5, and then z, and z can be any real number that you want. And that would be the solution to a dependent system of 3 variables and 3 equations. If I would have gotten a false statement here, I would have stopped immediately and said that there's no solution to this system of equations. And this wraps up section 6.3.